Okay, dear students, अब चलते हैं मैग्नेटिज्म लेसन 8. This is a very small derivation. We require little understanding. Current loop as a magnetic dipole. Before I proceed, let me explain this 3D model I have developed for you. Suppose this is a circular wire carrying current. Circular wire carrying current like anticlockwise like this. So when seen from the top, the direction of current is anticlockwise. So when seen from the bottom, from this side, it will be clockwise. From this side, it is anticlockwise. If it is anticlockwise, when seen from this side, it will be clockwise. And this will behave as a magnet where the upper side, this side, will behave as north pole, and this side, the bottom, will behave as a south pole. Means the side from which the direction of current is clockwise will behave as south pole, and the side from which the direction of current is anticlockwise will behave as north pole. Let this point is small a, this point is small b, this point is small c, this point is small d. Equal distance. The distance from here to here is r, the distance from here to here is r, the distance from here to here is r, the distance from here to here is also r, right? So I will explain with this model. I will explain with this model, right? Now let us begin. Current loop as a magnetic dipole. Consider a circular current loop like this. Consider a circular current loop. Let I is equal to current in it. Suppose when seen from the top, I have shown it here also. When seen from the top, this side is top, this side is your bottom. And this is the loop, this is the loop carrying current. When seen from the top, it is anticlockwise. When seen from the bottom, it is clockwise. These are the magnetic field lines. And I will explain why the bottom side behaves as the south pole and the top side behaves as the north pole. Therefore, this current carrying loop behaves as a magnetic dipole, means like a bar magnet. I will explain. How these lines of force are like this, I will explain. When seen from the top, suppose the current is anticlockwise. Therefore, when seen from bottom, the current will be clockwise. Therefore, the conclusion is the bottom of the loop behaves as south pole of a magnet. The top of the loop behaves as the north pole of a magnet. This I will explain. And this is the only small derivation. This is only the small derivation. First, let me explain this thing. How, if the direction of current is anticlockwise, then that side behaves as north pole. If the direction of current is clockwise, that is as seen from the bottom, that will behave as south pole. Let me explain this first, and then we will come back to this little derivation, right? Now, for this, we have to go back to magnetic effects of current. We have to go back to magnetic. I am keeping it here so that you can have a look at it. I will show it again also. We have to go back to magnetic effects of current. In magnetic effects of current from Biot-Savart law, what we had studied for a wire carrying current, I, if you are considering a small element here, a tangent here was your I direction of ideal, and this wire carrying current was behaving as a magnet. Suppose you are interested to find the magnetic field here due to this small element only. Then from the center of the element to this point, towards this point was your radius vector. From the center of this element to the point. And if this angle was theta, at this point, let it be P, the magnetic field, the small magnetic field due to this small element according to Barrett-Savart law was mu naught over 4 pi ideal sine theta over r square. So this can be written as ideal cross r over r cube. Ideal cross r will be ideal r sine theta. So 1 r will cancel, so we will be left with r square. So I am writing in this vector form because the direction of dB will be given by the direction of ideal cross r, right? That is, the direction of dB will be ideal cross r. Now look at this is your circular loop carrying current anti-clockwise when seen from the top, this side, and when seen from the bottom it is clockwise. Therefore this thing I have shown here. Let this point is equal to small a, that is this point at a distance r from here. Let this point is small b, which I cannot show it here, means it is above this point. This is your I. So here ideal is to this side. If this is the point, then from the center of ideal to this point, this distance is r, that is this point. And from the center of ideal to this point, this distance is suppose r. This point is same thing as this point here. And this point, which is I call it as, let this is A, this is A, this is B, that is just above it. This is C, and just below this point, that is this point, is your D. And all are equal distance. I have a point here at a distance r. I have taken ideal here. This is the circular wire carrying current. Here ideal is pointing to this side, tangent to it. This point is A at a distance r in the plane of it. This point is B. Is at a distance r from this point vertically upward. And this point is C, that is this point in the plane of it, but inside the coil. This is outside the coil, this is inside the coil. And this point is D, at a distance r from here, that is below this point into the plane of the paper. Now let us find out the direction of the magnetic field here, and here. Let us find the direction of the magnetic field at the point A, at the point B, at the point C, and at the point D, right? So that is what I am showing here. So for this point, if you consider ideal here, ideal is to this side, that I have shown here. And from the center of ideal, r is to this side, and the direction of the magnetic field dV is given by ideal cross r. So for this point, if you find out ideal cross r, ideal is to this side, r is to this side, means put a screw here, rotate ideal towards r, the screw will go into. So here the magnetic field is into. Similarly, this point I have shown here. For this point, I have considered ideal here. Ideal is to this side. That is, ideal is to this side. For this point, r is to this side. So for this point, the direction of ideal cross r will give you the direction of the magnetic field. So for this point, the direction of ideal cross r, if you keep a screw here and rotate ideal towards r, here the screw will come out. So here the magnetic field is into the plane of the paper. Here the magnetic field is perpendicularly out of the plane of the paper. Here the magnetic field is into the plane of the paper. Here the magnetic field is like this, pointing like this, pointing outward. And here the magnetic field is pointing inward. Similarly, here for this point, from here to here is r, and here ideal is to this side. I'm now finding out finding out for this point, which is above this point. Ideal is to this side. For this point, R is from here to here, from this point to this point. So ideal, the point is now above here. The point is now here. Ideal cross R will be towards this side, So here the magnetic field is to this side. Here the magnetic field is to this side. Similarly, if you find out here at this point, here ideal is to this side, which is same for all the 4 points. This as well as this. For this point, R is to this side. So ideal cross R will be to this side. So we have found out the direction of ideal cross R for all these 4 points, A, B, C, D. Here it is this way, 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 here it is this way. Means if you join this point, this point, this point, this point, this point with a circle like this, with a circle like this, the tangent at each point will give you the direction of the magnetic field. The tangent at each point will give you the direction of the magnetic field. So for this circular wire loop carrying current, when seen from the top, if it is anticlockwise, then the magnetic field lines are like this. Means it is entering from the bottom and coming out from the top. It is entering from the bottom and coming out from the top. It is entering from the bottom and coming out from the top. And in a bar magnet, we had seen the lines of force were entering from the south for the magnet, entering from the south and coming out from the north. And for this circular wire carrying current anticlockwise, the magnetic field lines are entering below the loop. So the bottom of the loop therefore behaves as the south pole. Therefore the top of the loop behaves as the north pole. That is the understanding. So the conclusion is the side from which the direction of current is anticlockwise behaves as north pole, and the side from which, that is below it, the direction of current is clockwise behaves as south pole. So that is the understanding. Now come back. So now come back to the derivation. This is the circular loop. From the top, the direction of current is anticlockwise. From the bottom, the direction of current is clockwise. I just took 4 points. Suppose this point is small a, this point is small b, this point is small c, this point is small d. Here the direction of magnetic field was to this side, here it was to this side, here it was to this side, here it was to this side. Means the lines of force are entering from the bottom and coming out from the top. So these are the magnetic field lines. And at the center it will be a straight line. At each point, here, for all other points, it will be circular loops. So therefore, since it is entering, these field lines are entering from the bottom and coming out from the top. Therefore, the bottom behaves as the south pole of a magnet and the top behaves as the north pole of a magnet. Means this wire carrying current, this loop carrying current behaves as a bar magnet like this. This side is south, this side is north. Right. Now it is found, let M is its magnetic moment. A is the area of this loop. It is found the magnetic moment is proportional to I, magnetic moment is proportional to area of the loop. Combining these two, magnetic moment is proportional to current into area. So magnetic moment is equal to some constant, current into area. If K is equal to 1, proportionality constant, M is equal to IA. Now, if the loop has n number of turns, this is for a single loop. If the loop has n number of turns, it will be n times IA. So So what is the direction? So this is what I have shown in another diagram. This is your loop carrying current I. Now when seen from the top, it is anti-clockwise. Therefore, the top of the loop behaves as the north pole. The bottom of the loop behaves as the south pole. Therefore, it behaves as a magnet. Behaves as a magnet whose magnetic, we know the magnetic moment is from south to north. So the magnetic moment is to this side. If the current would have been clockwise, then the magnetic moment would have been to this side. M will be equal to I times A, because if it is, when seen from the top, if it is clockwise, the top will behave as south and the bottom will behave as north. Means it will behave as a magnet where this is south, this is north. So the magnetic moment is this way. Right. So that is all about. You will not be asked this question, but for your fundamental of understanding, you need to know the direction of the current. If it is anti-clockwise on one side, then that side behaves as the north pole. If it is clockwise on the other side, then that behaves as the south pole. That you have to remember. And in the next lesson, we will see how an atom behaves as a magnetic dipole. In the next lesson, means at the center there is a positive charge nucleus. An electron is going around in a circular orbit. Since it is going around, there is current, and this also behaves as a magnetic dipole, and the derivation of this I will do in the next lesson. And hope this thing is clear to you. Have a look at it once more. Have a three-dimensional. This point is small a, this point is small b, this point is small c, this point is small d. Taking the direction of current from the top as anti-clockwise, I explained you the direction of the magnetic field here, 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 and also here. At all the 4 points I just explained. At this point, this point, this point, and this point. Into this way. Means it is along here to this side, here to this, here to this side, and here to this side.